Okay. Yeah.
So I guess you should see my my PowerPoint.
Yeah.
I hope it doesn't crash, because last time when I rehearse it at one slide, it always crashes for some reason.
I can see it very well. And can you move your mouse? Let me see if we can see your mouse.
So normally
yes,
you should.
I can see it. Okay, then
this
welcome.
meeting is live streamed. I got it. Yeah. Okay.
Yeah. On YouTube. Then welcome everyone to our weekly colloquium at the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is Dr. Mattia Walschaers, the Laboratoire Kastler Brossel in France. And let me say some few words on his vita. So Mattia Walschaers is a CNRS researcher at the Laboratoire Kastler Brossel in Paris. In 2016, he completed a binational PhD project at the University of Freiburg in Germany and the KU Leuven in Belgium. He then moved to Paris, where he holds a tenured research position since 2019. He works as a theoretical physicist in a team that mixes theory and experiment. His research concentrates on quantum states of light in the continuous variable approach. He specializes in the use of phase-space methods to study non-Gaussian states and their quantum correlations. Recently, he also started connecting this work to parameter estimation and quantum metrology. Mattia, thank you very much for joining us today, at least virtually. It's
a pleasure.
Yeah.
Thank you,
It's a
Thomas.
pleasure to have you again here in Cuernavaca. I think you visited us once.
I visited, when was it? In 2013. So it's, 8 years ago, more or less. So I think I even met you there. So
yes. I think we met first in Cuernavaca. Yeah.
Indeed, yeah.
And we're looking forward.
It's a pity not to be able to be there in, let's say, in real life, because I really liked my first visit to Cuernavaca. So it's anyway, let's say that this is the next best thing. So thank you very much for the nice little introduction. So I'm going to talk about, well, the title is Multimode Quantum Inspired Optics. So the name of the research group in which I work is Multimode Quantum Optics. And so I'm going to give you kind of an overview of our most recent activities, mainly focusing on the theory work. So I'm kind of in charge of the theory side in the group. And I will just give you a bit of an overview. And as you see, like we do also quite complicated optics experiments, which is this. So this is a picture of our optical table from a few years ago, and I'm not allowed to touch anything on there. So So I have to click somewhere, I guess. Yes, now it works. So the title had optics in it. So as you might have guessed, a lot of it will be about light. I guess the background of the people here is a bit varied. So I decided to start with something that everyone, or at least every physicist knows, is that light is basically a solution or a wave solution to Maxwell's equations. We do, we mainly do free space optics. So often when we talk about light, what we actually measure is the electric field of light. And so this is kind of the Maxwell equation that it satisfies. So in the title, I also had modes, so multimode quantum optics. So what are modes? This is a question that was recently asked on Twitter by Jeff Landin from Ottawa, who is a quantum optics researcher as well. And so he asked the question, what is an optical mode? And as you see, he got 41 replies. And so there was a lot of discussion going on because no one really agreed to what an optical mode was exactly. So I decided it was a good idea to give a kind of a definition to, at least when I talk about modes, what I actually mean. So modes, to us, what we understand in our group is essentially normalized solutions to Maxwell's equations. So normalized, and also in the sense that you can kind of construct a basis of modes, an orthonormal basis of modes, which you can then use to represent any solution to Maxwell's equations. And this is very useful because when you actually study kind of an arbitrary light field, an arbitrary signal, what you get is something like this. You have your electric field that you can decompose then in this basis of modes, this basis of normalized solutions of Maxwell's equations, where you have the mode appearing, and then you have some coefficients. And what we are often interested in is these complex amplitudes of the field in this decomposition, because they carry usually the information that we actually use for varieties of applications. And so often what we will try to do is find the right way of decomposing a certain signal in a good, well-chosen mode basis to extract the most information possible. So if you want to get kind of a visual idea of this decomposition, I like to always think of this image of the dark side of the moon of Pink Floyd, where you have white light coming in. It's a simple prism, so it's like the white light is fanned out in different frequencies. And you can think of this as doing this kind of modal decomposition. So the light comes in is this electric field E. Then you have the different frequency bands, which are the different modes, in this case, frequency modes. And the field then in each, or the amplitude, or the strength of the signal in each of these frequencies, this would be then related to these complex amplitudes. So this is the kind of physics, the kind of optics that we deal with in our lab. And let me introduce you quickly to our group. So this is at least part of the group. It's a recent picture, as you can see from the masks, but the sun is shining, which in Paris it doesn't do often in winter. So it's from a few months ago. And so we have three big branches of activities. Everything is a bit intertwined, so it's a bit hard to draw lines. But so one of the big activities that we have is quantum-inspired metrology, parameter estimation. Then another big activity is non-Gaussian quantum states. And the last big section is complex quantum networks. So here, I'm not going to talk about this part today in my talk, but let me just say that basically what we try to do in this part, so Valentina has Valentina, who is sitting here, has an ERC project on this, where we try to build networks of optical modes. So basically all these little nodes, they represent optical modes, and these optical modes can then be correlated, quantum correlated to each other, interact with each other in some ways. And so this is kind of the type of things that we are interested in this ERC project. So I already introduced you to Valentina, who is one of the two other permanent people in the group. So, and the last one, except for me and Valentina, is Nicolas Treps, who is sitting here, who is mainly piloting these two sections. And so this is also what I will talk about, because most of the theory work I've been doing the last year has been concentrated on this side. So let me start by introducing you to what we call quantum-inspired parameter estimation. So this is a very old problem in our group. So this all started roughly 20 years ago by Nicolas, when he was working on what is called the quantum laser pointer. And so the idea is quite simple. You have a laser beam, which is kind of Gaussian in shape, and it hits the screen, and it doesn't hit the screen exactly in the center. And the question is, where exactly, like how much displacement with respect to the center of the screen do you have? And so, of course, you could just take a picture and try to measure it, but this is something very imprecise. So what's kind of the most precise thing that you can do? And so the idea that they had was, well, we do multimode quantum optics. So let's use these modal decompositions of light to try to answer this question. And so you can take your electric field that you have, which is displaced. And the idea is actually very simple. So you have like this slightly displaced electric field. You want to know the displacement. So the field, you can think of this as just a shift D that you implement to the electric field that would be centered. And then you can do a Taylor expansion. So basically you have the non-displaced field here. And then you have a term proportional to the displacement times the first derivative of the field with respect to the position X. And then you also have all the higher order derivatives. But if the displacement is very tiny, you can basically forget about the higher order derivatives. And what is interesting here is that you can think of this Taylor expansion as one of these mode decompositions. So this is just like a Gaussian spatial mode, basically. so a profile of the normalized solution to Maxwell's equations. But actually, this first derivative of the electric field is, if at least because the field is Gaussian, this is also a well-defined optical mode. And then you have all the higher derivatives, which actually gives us a series of Hermite polynomials that appear. So you get a decomposition in what we call Hermite-Gauss modes. And so what we also see is that we can think of this factor here that is proportional to the distance as actually the amplitude of the field, or of this associated with this specific mode in the first derivative. So what this means is that if you can somehow isolate this optical mode and measure, for example, the intensity of the light in this mode, then you have access to this value d, and you can use this to estimate the displacement of your beam. And it turns out, this is what they showed in this paper, that you can, with the right type of detection techniques and so on, that you can actually like do much better than what you can do on a with a typical camera. So, okay. So the intuition that we gain here is that Hermite-Gauss modes are somehow good at doing distance estimation. And distance estimation is actually a very important problem in imaging in general, because there is this thing known as Rayleigh's curse that appears whenever you do astronomy, whenever you do biological imaging and so on. The idea is simply that you have two emitters, which are two good approximation point sources. They emit incoherent light, thermal light, let's say. And of course, usually what we do is we send this light through some kind of imaging system to be able to actually detect it on a camera or something. So this would be kind of what you would see on a camera. And this imaging system, the optics is going to spread out the signal. So even if you start from a complete point, you have this thing called the point spread function. In our case, we usually assume it to be a Gaussian or something, at least a good approximation. So you spread out the signal. And of course, at some point, these two blobs here, these two Gaussians are going to overlap too strongly for you to really like measure accurately the distance. So this puts a limit on how accurately you can actually estimate the distance between these 2 points. And so the question is somehow whether we can then now use our clever idea of doing mode decomposition on this kind of field. So this would be the electric field that we have on this side. Can we now find clever mode decompositions to figure out what this distance between these 2 point sources is, and to somehow beat this Rayleigh limit or this Rayleigh curse. And so we can use the intuition that we had from this quantum laser pointer to extend, to basically again use these Hermite-Gauss modes that we know are actually good at doing distance estimation. So here we can do the problem in 2D if we want. And so then we have basically like our Gaussian mode at the center of the screen. And then we take all the higher order derivatives, both in the X and the Y direction, and we get this kind of basis of optical modes. And so the idea would then be, if we can measure the signal in sufficiently many of these modes, or maybe in all of them, if we do theory, like we say that we have access to a full basis, infinitely many of these modes and all of these amplitudes, how well can we then like estimate the distance? And it turns out that in principle, this works extremely well, in the sense that for incoherent sources, you can actually show, using techniques from quantum information theory, that this saturates so-called quantum Fisher information, and that this is like really the best thing you can possibly do. Like you cannot do with this signal, given that you have two incoherent sources, you cannot do any other measurement, whatever you do, that does better than this kind of modal decomposition. But here I put the word in principle in red, because this indeed assumes that you can like really do everything perfectly, measure infinitely many modes, you count photons in these modes and so on. So what we do, we're at least in part an experimental group, we want to figure out how to actually do this in practice. So in practice, such parameter estimation, what you do is you take some observable that you measure many times, and you would look at then the average of your many measurements. So for example, this could be the photon number, and then you measure, when you measure this average, the intensity of your light. And so what we want to know then is some kind of calibration curve. So this is something that we usually get from theory. So basically, when we know the average value of the observable X, like the average intensity, for example, how does this change when we change the parameter D? And then we have, so we can say, if we know this curve, we can look at the measurement that we had, we can trace it over this curve and see, okay, this corresponds to this value of the displacement. But then, of course, the tricky point is that whenever we do these measurements, we also have an error on them. And so this error bar will also propagate. And the question is, what exactly is the size of this error bar? This is a very simple exercise that every experimental physicist probably already did. We know from the central limit theorem that the error on this average that we measure, if we have many measurements, is behaving basically as a like this. Well, the average is basically kind of behaving as a Gaussian distribution, and the spread on this Gaussian is given by the variance of our observable divided by the number of measurements. So then, of course, we know how to calculate this error bar here, but then the next step is to see how it transforms when we trace back the actual value of the parameter. And this is, I have to click. So this is what you can do via some standard error propagation formula. You get that this error on the parameter, on the distance, it will depend on the variance, the fundamental variance on the observable that you're measuring, the number of measurements that you do, but then also on how this average changes with the parameter. So the steeper this function is, the better. This is somehow what you see also on the figure. The function is very steep, so you see that the error is ultimately quite small, but if it would be a very flat function, we would have a very large error. So the idea is that we have to find observables for which this calibration function is very steep. So, okay, so this is kind of how parameter estimation works. The next thing I told you was that in principle, what is the best thing to do is to do this decomposition in these Hermite-Gauss modes. So this is somehow what these modes look like. So we want to find a way of getting this signal in and transforming it into basically kind of different signals for each individual mode. So we need something which is kind of like a spatial mode demultiplexer, a device in which we put in the signal and in which we get basically, in this case, I have 8 modes, so where we get 8 signals out corresponding to each one of these 8 modes. And so if I do this, or at least we can do this because there is a company that builds a device that does exactly this. This company is called Skylabs. It's situated in France because it's a spin-off company of our group. So the funny thing is that they founded this company with the idea of doing telecom applications and so on. And ultimately they developed this modes multiplexer and demultiplexer, which we now again use in our research. So this is what it looks like in practice. So the idea is that you get a signal in here. So this would be kind of the field here that we are interested in analyzing. And what we get out here is actually there are 8 fibers, optical fibers going out, and each fiber carries a signal corresponding to each one of these modes. So this device exists. So how do we then in practice use it? Because the parameter estimation that I introduced was we measure one observable, we look at the average and so on. But here we actually have a bunch of different modes. So we measure multiple observables. And so the thing that we can do, or that we are going to do, is we are going to measure each one of these modes. We are going to measure the number of photons in these modes, or actually we are only going to use the average number of photons in each mode. But so we use this as our observables. And then we are going to combine these different data with a coefficient. So we are going to take the sum of each intensity in each mode multiplied by a coefficient and group them together. And this jointly gives us our observable. So Manuel Gessner, who actually I think Thomas may have also met in Cuernavaca back in the day. So he joined our group. Well, not actually our group. He joined our lab as a postdoc, as a kind of independent postdoc a few years ago, and he worked on this problem in a bit more, in a bit of a different setting. But the idea is that actually he designed or developed a method for finding or he could show that for every value of the parameter of the distance, there is basically an optimal choice of coefficients that you can calculate analytically. And so, the intensity that, or the sensitivity that goes with this optimal coefficient is given by this formula. So it reminds you probably of an error propagation formula, where now we're not going to only look at the noise in each one of these observables, but we also look at the covariances, so how the different detectors are correlated. So this is this matrix that pops up here. And then you have, again, these contributions. So what we are interested in then is to see like which of these observables or these intensities in each mode, how they change with the parameter. And of course, we want to ultimately give a high weight to the ones that change the most with the parameter. And this is a very subtle thing because it's distance dependent, for example. So for every value of the parameter, we get actually a different optimal set of coefficients. So you have to have an initial guess of what your parameter will be. You choose the coefficients, then you get a better estimation of the parameter. And so you can iterate this a few times to get like the best possible precision. But also from this formula, so you have actually an analytical way of finding exactly what these coefficients are for the parameter. And so then the actual noise on the distance that you would measure is given by 1 over the square root of the mu, which is the number of repetitions of your measurement, multiplied by this sensitivity here that was analytically determined. So this is the sensitivity or the noise that we will get. And so we could identify this in another way as basically the smallest possible distance that we can resolve, because this is the value where the signal to noise ratio becomes 1. If distances are smaller than this, basically the signal is completely lost in the noise and we cannot resolve anything anymore. So this is how we are going to analyze the data that we get from this spatial mode demultiplexer. Then there is another problem, which is actually that we want to really have a realistic setup, and a realistic device usually doesn't do exactly what you want it to do. So there are many errors and imperfections to take into account. And once you do metrology, parameter estimation, these imperfections are actually important to know and to study. So this is the work of our postdoc Giacomo Sorelli, who analyzed all of this. Again, it's quite remarkable how many of these things could be done analytically. So first of all, the first error source that we take into account is misalignment. So we assume typically that in the input of our mode demultiplexer, the two sources are kind of exactly symmetric around the middle of the screen, let's say. And this is in general not really the case. So we can look at what the effect is of a little displacement here. Then the next important source of error is crosstalk. So ideally, every output fiber should correspond exactly to one of these modes in this decomposition. But I mean, this is a passive optics element. It really works with just, it's like phase screens and so on, on which you bounce the light back and forth. And this is never working. It works extremely well, but it doesn't work perfectly. So there is always a little bit of signal that you detect in, for example, the mode 1,0 that actually comes from some other modes. And so we have to take this into account. And then finally, there is kind of a golden oldie, which is dark counts. Sometimes your detector clicks, registers a signal that is not actually coming from the source, but from, I don't know, it could be electronic noise, it could be stray light. There are many, many reasons why you would detect photons that are not really in your signal. So I'm not going to go through all the details here of the calculations. I just want to show you the results that come out of Giacomo's work. So again, all of this is analytical calculation, so at least much of it. So what you see in these plots are, first of all, there is a green line that appears in every plot, which corresponds to perfect direct imaging. So it's like saying that you have a perfect camera with pixels as small as you wish, how well can you resolve ultimately the distance of this between these two sources using an ideal camera without any noise? You see, of course, this like the smallest distance that you can resolve. So this is what we show here. The smallest distance that we can resolve goes down with the number of photons that we detect, but it goes down much more slowly than the black line, which is somehow the best thing you can possibly do. So this is the ideal result for this demultiplexing in these Hermite-Gauss modes. So this works much better, but it's of course an idealized case. And then the real signals that we would get, and let me kind of discuss the case where we have all the noises included. Well, the real signals, you have to make a difference between the case where you have a very faint source that only emits very few photons, and you just detect many of them, so you do many repetitions of the experiment, and the case where you have a very bright source, but you don't detect many photons, or many repetitions of so you have the same number of detected photons in both cases, but the scenario can be quite different. And the reason for this difference, so if we take all the noises together, we see that the blue line, where we have the very faint sources, it's actually even worse than the direct imaging. It's really not a good way of functioning. And the reason is, when we look at all the different individual noise sources, is basically that the dark gowns are going to kill us. And this is quite logical, because what happens in these modal decompositions is that you say, if you have extremely small displacements, you are going to say, okay, if there is no displacement at all, you just have one Gaussian. And then if you have a very small displacement, you have a contribution from these higher derivative modes. And so there is a difference between having no signal at all in this mode and having a tiny signal. And this is this tiny signal that you get, then all of a sudden you can use to very accurately estimate the distance if there is no noise. But if you have dark counts, if half of the time the photon you detect is actually not coming from the signal, this completely kills your sensitivity. So this will not work. On the other hand, if the dark counts are much smaller compared to the signal that you have, as is the case for the very bright sources, then you see that actually things work much better. Specifically, the dark counts are not at all a problem in this case. However, what is going to be a major issue is the crosstalk. Well, crosstalk is a bit complicated because usually it's very hard to characterize exactly which modes are coupled to which modes and how much is going into which mode. But we can know more or less orders of magnitude by characterizing the device. And if we know these orders of magnitude, we can basically do many simulations of random crosstalk matrices. And then we see basically, like, the red line would be the average here. But then there is a gigantic spread on the average. So you see that you have some cases of crosstalks where things get really very bad. But what is interesting is in this regime where you actually have quite few photons detected. So this reasonably weak intensity regime still, here you have this kind of sweet spot where you still do super resolution imaging, even with all the imperfections included, where you can still resolve distances that are much shorter than what you get for the direct imaging case. And then what this kind of teaches us is that if you have very intense signals, you don't have to spend too much time to optimize the detectors. We probably have to take a lot of care of doing a good alignment still, like a sufficiently good alignment. And we probably have to really know well what the crosstalks are. So this is the take-home message. So a lot of things that we are doing now, we are building the experiment, is figuring out ways of analyzing exactly in our device what these crosstalks are, and to get them to know them as precisely as possible, so that we can actually correct for them or take them into account. And so this is the work of our PhD student Clémentine. So she is building the experiment. And then we also have recently a new PhD student, a theoretician, Ilya, who joined our group. And he is working more on the cases where you do not have incoherent sources. So we have looked a lot on, like, everything is done for incoherent sources that emit thermal light. But actually, so Ilya's work is looking at what happens when we have more exotic quantum states there. What happens when we have maybe fully coherent light and so on. How can we benefit from this and all these kind of things. So he has some nice results at the moment. I don't have time to talk about them, but I show you the reference at the end if people are interested. And so now I think I'm roughly halfway through my talk, so I will switch to the second part, which is about non-Gaussian quantum states. So what we did up to now was classical optics, a bit inspired by quantum techniques. What I'm going to talk about now is, let's say, hardcore quantum stuff. And so I want to show you, first of all, what the link is between non-Gaussian states and how we can produce non-Gaussian quantum states with the help of Gaussian quantum steering, Gaussian quantum correlations. And so what we do in our group when we do quantum experiments, quantum optics, is we use a continuous variable approach. So this means that our modal decomposition, so our observables, which is light, is now going to become a quantum observable. But what really becomes quantum in this modal decomposition is not as much the modes. The modes, they are kind of the physical system that carries the information. But what is quantum, or what is the quantum observable, is actually the amplitude, the field in each mode. And when we do continuous variable quantum optics, we are not going to care about the photons. We're not going to count photons, which is kind of the energy that is in the modes. But we are going to focus on the fields themselves. So we are going to specifically have an observable, which is the real part, and an observable, which is the imaginary part of this complex amplitude of the field. And in optics, it's kind of, you can take any kind of combination. You can like turn them and take observables, which are like the sine of theta times one plus the cosine of theta times the other, and so on. But let's just talk about Q and P for the moment. And so in this dark side of the moon image, what this means is that every color here, every frequency is going to acquire an observable Q and an observable P. So apparently there are 6 bands here. I never counted them up to when I made this talk. And so these different observables, they satisfy the Heisenberg or the canonical commutation relation, which means that they really behave as position and momentum operators in mechanics. So of course, here in optics, like physically, there are very different objects, but they have the same mathematical properties as position and momentum, which specifically means that we can represent them, for example, on a phase space. Phase space, which would then represent the possible measurement outcomes for these observables. And the reason that we call it continuous variable approach is that, as in position and momentum, these observables can actually take any possible value on the real line in principle. And of course, we have finite energy, so there are some practical limitations, but mathematically speaking, they can have any value. And so the quantum states are then the objects that are going to determine how the noise that we measure in these observables is actually going to behave. And this is usually something that we represent by Wigner functions on phase space. So I didn't know whether everyone would know what a Wigner function was, so I give a quick introduction. You can go very technical about Wigner functions, but the idea is that it's kind of, ideally you would want to represent on this phase space of measurement outcomes for the Q and P operators, you would want to represent a joint probability distribution. But because Q and P do not commute, you cannot jointly measure them. And kind of a signature of this lack of joint measurability is that you cannot, in general, for any arbitrary state, represent the state by a joint probability distribution on the phase space. But you have a Wigner function, which then is a function that basically correctly represents all the marginals. So for example, if let's say that we just have one mode, we have an observable Q and an observable P. So the Wigner function is defined on the set of possible measurement outcomes for Q and P. And if you integrate out P, you obtain the probability distribution for measurement outcomes of Q. And if you would integrate out Q, you obtain the probability for P. So this is one of these states where you clearly see it's not a probability distribution. It has negative values. But if you integrate, you get these nice probability distributions that look like this. So this is, if anyone is interested, this is what people call in optics a Schrödinger cat state. Then there is one class of states that is very important, which are the Gaussian states, and they are kind of, not surprisingly, the states for which the Wigner function is a Gaussian probability distribution. And so these states they have some quantum properties in the sense that you can kind of compress them very tightly in one quadrature, so have very low noise in one, and you pay, due to Heisenberg's uncertainty relation, the price on the other. So this is somehow a quantum feature, but ultimately, to me, as kind of someone coming from more, let's say, a mathematical physics background, what is really quantum would be the cases where this Wigner function is not at all a probability distribution. And so the reason why these Gaussian states are very important is because they're somehow accessible. They can be deterministically produced in experiments. So this is one of the main reasons why we are interested in continuous variable systems, because you can use them to make very large entangled states. So this is an example of that is produced in the group of Akira Furuzawa. More or less the same kind of states are produced also in Denmark by the group of Ulrik Andersen. And the idea is, what you see here is a kind of a network of modes. So every point here represents an optical mode, and every connection here represents an entanglement link. So this is a gigantic entangled state. People make and control these states using kind of temporal multiplexing techniques and so on, of thousands, hundreds of thousands, millions of modes. The only thing that limits them is that at some point they have to turn off the experiment to stop. So they can go on forever, at least it's what they say. And then you have other kind of ways of realizing the same kind of states. But the problem is that all these states that they make like this, they belong to this class of Gaussian states. So they use this idea of squeezing, where you can get very low noise in one quadrature. This is kind of a quantum property in the sense that in a mathematically strict sense, you can get quantum entanglement in this way. But the problem is that everything that you do with these Gaussian big entangled states can be somehow efficiently simulated on a classical computer. So in quantum information applications, we usually want to have a quantum advantage, something that you cannot simulate. And for this, it turns out like this paper shows very generally that you need actually up to some assumptions that you need to have this kind of negativity in the Wigner function, because if you do not have it, you can write down an efficient algorithm to simulate everything you do. So what we try to do is make such quantum states, or actually combine both of these ideas. And so the way we do this is we take this kind of multimode light. Actually, we also use frequencies in these quantum experiments. So we also have this kind of, literally these it's diffraction gratings that fan out light in different frequencies. So, and the idea is that we will give some of these frequency modes to Alice and some of these frequency modes to Bob. Of course, this is all just on one optical table, but it's to give you kind of, to just give names to things. What Bob is going to do is we are going to do a measurement on this side of the system. We can do any measurement we want. So like we can here assume that this is the most general thing you do. You can count photons, measure parities, project on the weirdest state you can imagine. And then the idea is that you are going to like measure some observable and post-select on a certain outcome. So Bob is going to say every time, okay, I got outcome B. And then only then Alice is going to keep measurements. And the question is, when Alice would reconstruct the quantum state that she has with this conditioning, what is the state going to look like? What's the kind of form of the Wigner function here? And so actually we could derive a kind of, actually it's only later that I realized that it's kind of a quantum version of Bayes' theorem. And so what we get is this expression, which is quite intuitive somehow. So what you have at the bottom is the success probability of Bob. So Bob will get his outcome B with a certain success probability. So this is kind of the expectation value of a POVM element, of a projector, if you wish, something like this. And then here what you have appearing is the Wigner function of Alice. And so what we assume here when we derive this is that actually, well, actually you don't, the weakest possible thing that you have to assume is that the Wigner function of Alice is an actual probability or an actual probability distribution. Actually, you have to assume that the global Wigner function for Alice and Bob is a probability distribution. There is no Wigner negativity in the system. So typically in experiments, this is going to be a Gaussian state. And so then, so this is what you get. So this is really behaving as a probability distribution on the phase space. And then you have this kind of funky thing appearing, which is a kind of quantum conditional probability. And if Bob does a measurement that is sufficiently exotic, this can actually be negative. And so this is why I put it between exclamation marks. It's not really, but it's not really a real probability. So the point is that this is somehow representing the fact that actually, like, this would be what you get if you look at the probability that Bob obtains a certain outcome, given that Alice selected a specific point in phase space. But because you cannot measure X and P or Q and P at the same time, you cannot actually physically measure one point in phase space. So you cannot do this selection like physically, and this is why the laws of quantum mechanics give you negativities here. But the funny thing is that this gives us an answer to a very general question, is when is the Wigner function on Alice's side going to be negative? Well, there are some conditions on the measurement that Bob does, but in general, like if we allow Bob to do whatever he wants, the point is that we have to answer the question, when does this conditional probability, this quantum conditional probability become negative? When is it not a well-defined probability? And you can prove somehow that this can only be the case if there is a very strong quantum correlation between Alice and Bob in the initial state, so not before Bob does the measurement. And this correlation has to be a correlation where Alice can steer Bob's measurements. So the proof is not very complicated, but it's a bit subtle, and there are some technical things that I would have to introduce. So I decided to not really go into the technical details of this, but I wanted to more explain you what this steering actually is, what it means, and where it comes from. So quantum steering is something that happens when, well, you have, again, Alice and Bob, and you allow Alice and Bob to do arbitrary measurements, and they are going to follow a certain protocol. Alice is going to tell Bob, I am going to measure, for example, observable A1. Then Bob is going to decide, okay, whenever Alice is measuring A1, I'm going to measure B1. Then the next step is that Alice is going to tell what measurement outcome she had. And Bob is going to keep then all the data, or group all the data where Alice had a specific measurement outcome, or a specific set of measurement outcomes, if you wish, but this is what they are going to do. This may sound a bit abstract, but it's somehow more accessible when you visualize it with histograms. So for every possible measurement outcome of A1, Bob is going to create a little histogram that corresponds to the cases where Alice measured this outcome. And Bob can then decide, whenever Alice is measuring the other observable A2, that he's going to measure B2, and he gets the same set of histograms for that case. And so the question of steering is somehow, when can Bob see that there is entanglement by just looking at these histograms, by not trusting Alice? Because maybe Alice communicated that she was measuring quantum observables, but she might just have a computer that is sending random numbers to Bob. So this is something like, can we actually check this? And the answer is yes. There are many techniques and many ways, but the simplest and most intuitive one is to say that you're going to take these histograms on Bob's side, and Bob can look at the variance of every histogram. And then Bob can combine the variances of these different histograms for the different outcomes and average them together, taking into account the probability that Alice had a certain measurement outcome. And this way you get this kind of general conditional variance or inference variance for B1, given that Alice measured A1. And you can do exactly the same thing to get such an object for the case where Alice measured, where Bob measured B2 and Alice measured A2. And then, of course, if there wouldn't be this conditioning, Bob would just have the variance of B2 and the variance of B1, and you would have Heisenberg's uncertainty relation, or let's say the more general uncertainty relation, that would tell you that in principle, like this product of variances would always have to be bigger than the expectation value of the commutator of these two observables. So you want ideally to choose observables that very strongly do not commute. But so in the case of sufficiently strong quantum correlations, you can actually have a case where these conditional variances do not satisfy this uncertainty relation, and where actually you find a value that is smaller than what would be allowed by Heisenberg's uncertainty relation. And it turns out that this is also, if you have only classical correlations, you also get something like Heisenberg's uncertainty relation, where this is always larger than this expectation value of the commutator. So this is a sign of quantum correlations. And so this is what quantum steering is. And so this is what we need to get this Wigner negativity. And without knowing it, we actually implemented this thing in an experiment. So what we did experimentally is more something like this. So we do multimode experiments where we have sets of modes. We could call them Alice and Bob. We have something of a case where it's more like Bob is measuring one mode, which is only very weakly coupled to the rest, but still we are going to count the number of photons that Bob has there and just select the case where Bob had exactly one photon. So this means that Bob is going to still keep a little bit of signal, or still has some modes in his with him, and Alice also still keeps her modes. And so this is the context more specifically of photon subtraction, which you can think of as like you create an entangled state between Alice and Bob. You have something going to Alice, something going to Bob. So this is an EPR state to people who know a bit of quantum optics, who know this jargon. And so the idea is that like there is entanglement between a mode that Alice has and a mode that Bob has. And Bob is going to then couple his mode very weakly, like take out a little bit of light and detect the photon. And this is how they do photon subtraction, because if there is a photon detected here, you know that in the light, generally there is one photon missing somewhere after this detection. And so we measured in our experiment, we generate this kind of states. We check indeed that we have, so this is a way of checking this quantum steering. You don't have to really mind the symbols. This is a value. If there is no steering, it should be larger than 2, but we have something which is smaller than 2. And indeed, we also have, when we do our measurements, we have Wigner negativity, very weak, but it appears. And so what we see is indeed that actually, when there is this steering from Bob to Alice, so that Alice's state, when we subtract the photon on Bob's side, is going to become negative. On the other hand, on Bob's side, nothing negative is happening. So really, Bob is doing this photon subtraction, and Alice is getting all the negativity. At the same time, we also did the inverse experiment. So if Alice would do the photon subtraction, Bob would get the negativity. And so this kind of it confirms it's consistent with this very much more general theory work that we did. So this is an experiment that we did essentially 2 years ago, and actually the theory work we only did later on, trying to figure out like when does negativity go where and so on. And we then realized that we actually had an experiment that showed what we did in theory. So I don't know how much time I have left now. I wanted to explain a little bit about what happens then to the steering after you do the non-Gaussian operation.
You have about 5-10 minutes. So.
Okay, I will. I think this should probably be enough. You stop me if I take too long, but I think
go ahead.
So the idea then is, so now we've talked a lot about, you have steering in the initial state. This can help you to create interesting non-Gaussian states on Alice's side. But so now the interesting thing is, of course, that actually with what we do in the lab, when Bob only measures one mode here, you create this kind of Wigner negativity, these non-Gaussian features On Alice's side, and also in the global state, we actually have another work to show that this is like globally, you always have more negativity than locally, which is kind of, it's not very surprising somehow. But so the idea is that like Bob still has some modes. And so we know, or we knew that there was steering before between Alice and Bob. And so the question is, after this photon subtraction, is there still steering between Alice and Bob? And how can we measure this? So back to the basics of steering. Now you see that I did an effort to make the statistics here in one of these measurements really non-Gaussian. So this is like clearly statistics has changed when you do this. And this kind of nicely illustrates that when you now are going to look at variances, as long as everything is Gaussian, the variance determines in principle the full statistics. However, once you have non-Gaussian features, variances wash out a lot of interesting information. And so when you are going to use this kind of inequality, you have the choice of either, like you could try to measure very non-Gaussian, very exotic observables, but this is in practice very complicated. So the question is there a better and more useful inequality to use for non-Gaussian states? And so the answer is actually going back to the very beginning of the talk. Actually the answer is that we can use parameter estimation techniques. So this is again something that was developed by Manuel, or at least in a very general abstract sense. They came up with an idea that turned out then as a next step to be very useful for our experiments. So the idea is that you're going to implement a parameter on Bob's side. So basically, you're going to kind of do something where you manipulate Bob's measurement. So you change some kind of a parameter. And the idea is you're going to try to estimate this parameter as accurately as possible. And so what they showed is that there is this kind of conditional relation where you have the quantum Fisher information appearing. So what is this beast? Well, the point is that you're going to try to estimate the parameter theta that you implement on Bob's side, and you have a certain noise on this, and you can formally, like the quantum Fisher information is somehow the best you can possibly do. Like you have Bob's state with this parameter implemented, you are allowed to do any possible measurement. What is the best estimate of the parameter that you can get? Well, the best estimate is given by the quantum Fisher information. So here we, of course, take into account that we are actually dealing with conditional states. So we are looking at the case after Alice has measured A1, we look at how well can Bob estimate in principle this parameter theta. And so in this inequality, we're going to replace this variance by 1 over this Fisher information, this quantum Fisher information. Then we also have to replace the variance on the other side by another variance, but it has to be related to theta. So Bob has to choose an observable B, which is actually the generator, somehow, if you wish, the Hamiltonian that is going to implement this shift in the parameter that is going to transform the state with respect to the parameter. If this is a clock, this could really be the Hamiltonian that implements some kind of dynamics, for example. And then if you combine these two quantities, the inequality becomes simpler. Once you show that the product of these two things is smaller than 4, you can be sure that there is steering between Alice and Bob. So this is a metrological approach to quantum steering. And it's a very beautiful result. I'm not a co-author, so this is really work of Manuel. I really love this result. But so what we then did is, well, we wanted to use this, but we were confronted with a problem that actually the quantum Fisher information is something that's ridiculously difficult to calculate. And so with our master student, Carlos Lopetegui, we had this idea of rather than looking at the quantum Fisher information, to look at the Fisher information of a well-chosen measurement. And so you have this kind of series of inequalities. The idea is that if you would, so here you try to estimate theta using all the statistics of a certain observable B1 that you measure. So like using the full histogram rather than just the the variances. And basically the quantum Fisher information would be kind of maximizing this quantity over all possible choices of B1. But what we had in mind is we just have to find one that works sufficiently well. And ideally, we wanted to find one, we wanted to do this with homodyne detection. And to our surprise, this actually worked. So the idea is that now the observables that you are going to measure are not just some arbitrary complicated things that Alice and Bob can measure. No, Alice is going to measure Q1 and P1 and so on. And Bob is going to measure Q4 and P4. So they both measure these quadrature operators. But we are going to use the full statistics. So if we have non-Gaussian states, the statistics can have a lot of exotic non-Gaussian features, and we want to use all of it. And so the other nice thing is that we can use a parameter which is interesting, which is a shift in the average electric field, which just corresponds to literally taking this histogram and shifting it over a certain distance. And this is something that we can even do in post-processing. So this is useful because implementing a parameter is typically quite tricky. The nice thing as well is that if we shift the histogram of Q, that the observable that generates the shift is actually the momentum operator, the P operator. So if you measure Q and P on Alice's on Bob's side and on Alice's side, things should work out. And so this is the inequality that we use then in practice. For some reason, we took the additive one rather than the multiplicative one. And the idea is that if you can somehow show that the difference of these two quantities is larger than 0, that you have steering. So we tried this for the states, the type of states that we use in the lab. Of course, we took theory models of them to have them very clean, to see in principle whether this would work. So for completely pure states, when you do this using only variances, so using this very old idea of Margaret Reed, you see that actually steering from Alice to Bob, you can still detect, but if you want to do steering from Bob to Alice, so from the side where you subtracted the photon to the side, the other one, there you don't have anything at all that you see, like the dashed line is really here at the bottom. So we see no steering using variances, but when we use this metrological parameter estimation technique, we actually see that this curve shoots up, and we actually see a larger violation or a larger value, if you wish, for the case for steering from Bob to Alice. And so what this shows us is somehow that there seems to be a lot of steering going on. There seems to be a real advantage with this parameter estimation when we use these correlations. It's another way of interpreting these things. But it only appears when we really use the full non-Gaussian statistics in these quadratures. And so this is kind of a real signature of some non-Gaussian quantum steering going on. We also have another remarkable feature, which is that it actually goes down much faster when you add losses. So the more loss you have on the system on both sides, you see that this kind of non-Gaussian steering goes down very quickly, whereas the Gaussian steering, even though it's smaller in the ideal case, it actually survives longer. And so we worked a lot on ways of kind of making this practical. So for continuous variables, you have to take into account that actually you can never really post-select on one variable, but you have to take kind of an interval and so on. And so we took into account the fact that we only have access to finite numbers of measurements. But even taking all of this into account, we could show that for realistic values of the noise, like 5–10%, well, realistic, it's a bit optimistic, but still it's something that is not completely crazy, that you can get several orders, like standard deviations of violation or of beyond 0 for this witness. So in principle, this really gives us a way to measure, to see non-Gaussian quantum steering. So it's not yet on the archive. We're working on the paper now. So in a few weeks, hopefully you will be able to read it. And that is everything I wanted to present. So conclusions, very quickly, what you should remember is that I talked about super resolution, and I showed you that even in a realistic setting, this kind of mode demultiplexing technique can outperform the direct imaging of a camera. Then I also showed you that we can create Wigner negativity through Gaussian steering, and we use this kind of quantum version of Bayes theorem, Bayes rule to show this. And then finally, I showed you that we can also use these ideas from parameter estimation to then actually detect non-Gaussian quantum steering. And with this, let me thank the members of my group, in particular, Giacomo Sorelli, Manuel Gessner, and Carlos Lopetegui, whose work I presented. And also give a quick shout out to Ilya, who has just joined us and who is also working on the parameter estimation. So he really recently put a paper on the archive on using coherent light sources rather than incoherent ones and what you can do with them. It's really nice what you find. It's somehow very insightful. So if you're interested, go and have a look. And so with this, let me show, like, these are basically all the papers related to what I talked about somehow. And I have published this tutorial on non-Gaussian states mainly in quantum optics, but also a bit more generally in continuous variable systems, which is in PRX Quantum. So if you're interested in the things I talked about, definitely check it out if you want to learn a bit more. And so with this, let me thank you, all of you, for your attention and for inviting me, for having me. It was a real pleasure, and I'm looking forward to your questions.
Thank you very much, Mattia. Thank you very much for this very interesting, very clear talk. Are there comments, questions from the audience?
So let me maybe just say already also, like, I didn't really talk much about experiments, but if there are people who want to know more about this, I could go into a bit more detail there as well if there is some interest there.
Let me start with a very simple question. So in the first part of your talk, where you discussed this determination of distances of two beams, about which distances are we talking there?
This is actually a good question. So I didn't really emphasize this point, but so what you see here when we talk about distances is that there is always this W appearing, and
Exactly.
W is basically the width of so everything is kind of renormalized with respect to the point spread function. So this is basically how far is this Gaussian spread out. And of course, when you talk about astronomy problems, ultimately you want to translate this to distances which are well, if I guess what would be the order of magnitude, it would be like astronomical units. Of course, when you do like biological sampling, this would be, I guess the tricky thing when you talk about biology or biochemistry and so on is that when you talk about molecules, once they are too close together, you cannot really think of them as incoherent sources anymore. Like if you irradiate them with some light that they re-emit, if they are close together, they will interact, and so there might be a lot of exotic. So the distances cannot be like, once you talk about nanometers, like I guess there's too much chemistry and so on that you have to take into account, or biophysics. So I would say it's probably like it's smaller, like around the wavelength of light, like maybe a little bit less than hundreds of nanometers. So a bit less than yeah, that's the kind of orders of magnitude that you have then in mind there. Like, let's say any length scale is where it's sufficiently safe to neglect the interactions between molecules. So we work together with a group that does this, and they use these kind of nanobeats. I have no idea how they work, but yeah.
So will it be, or may it be possible to construct by these methods a better camera, or use somehow post-processing for data of a camera to increase the resolution of images?
So I think the problem here, it's a good question, but I think So what you could do in principle is, if you really have many modes that you measure like this, if you really have a large number, you could in post-processing recombine them in a correct way. And I don't know whether somehow, I never really thought about whether this would then, if you reconstruct this, give you somehow a clearer image, or like whether this allows you to I guess it should definitely allow you to compress data. So like this, I know because we have some other work that we did with the people from Skylabs analyzing their devices. And what we often do is work in kind of a pixel basis, where you have, let's say you have your Gaussian beams that go in, or like whatever kind of spatial structure that goes in. You represent it really as a picture with many pixels. And actually the problem that we had was it was way too big in data to actually put into a computer. So what we ended up doing was representing it in these kind of Hermite-Gauss mode bases, or cleverly chosen bases, to reduce the size of the images. So I guess probably I don't know much about image compression in computer science. So I would be surprised if some of these techniques weren't already used. I guess this is like wavelets and so on. They kind of do this kind of things. I guess so. They choose other bases. Probably there are more suited bases for doing this kind of things. But yeah, what we really want to do is so this idea of parameter estimation is really, it works well when you do not want to have like an image is somehow a gigantic amount of parameters. And parameter estimation works well when you have a very small amount of parameters that you want to know extremely well with high precision. And so like, for example, if you want to have, if you have exoplanets, you have a star and a very faint planet next to it. A very interesting problem is, and so Cosmolupo is working on this, like, how do you actually know, can you use these techniques to decide whether there is one object or two? And so there is a whole theory of this quantum decision theory, hypothesis testing, to do these kind of things. And then you could ask the follow-up question, how do you determine the distance between these two, this planet and this star, for example, or between two binary stars, these things. But so there, the distance is a very important parameter, and you don't really care too much about other things. You can do multi-parameter estimation, but like once you have a really large amount of parameters, I guess this, I'm not sure whether this is the most appropriate framework. I don't want to insult anyone doing quantum imaging or this kind of thing. So I don't, I've not really given this sufficient thought to give a clearer answer than this. So.
Okay, I see. There is a question from Alfredo Herrera. Alfredo, if you like, you can switch on your microphone.
Okay.
Alfredo, are you here?
Yes.
Yes.
Thank you. Very nice talk, Mattia. My question is related to measuring distances in astronomy. Suppose you are pointing to two sources in a galaxy. My question is if your method can be applied to measuring the distance to the galaxy first, and then to 2 points, to two sources in the galaxy, within the galaxy itself. And if the precision could be improved in comparison with actual methods.
So there are several questions here. So, okay. So the first question, I guess I could translate it to kind of more generally speaking. What I talked about here is I have two objects, and I have basically I want to know how far they are from each other. But the question now is, can I measure in the Z direction, right? And the answer is in principle yes. So you can then it depends on what kind of how much information in your images you have to use that you can use somehow. If you have so what we looked at, actually we did a kind of a previous experiment. I'm saying we, but I wasn't really involved. But where you have two sources that can really move in a three-dimensional plane. And where you actually really want to see like they do not only move like in this kind of projective plane that you look at, but they can also move in the Z direction. And there is indeed a way, like you can use similar techniques to estimate this distance in the Z direction. So I guess if you have, I'm not sure if you have only one source, like if you have something that you consider a point, whether it would work as well. I guess then, well, it depends a bit on there. I'm more like I'm a quantum optician with a big quantum and a small optician. So I'm there. You have to really think about what the optics is and so on, and how the beam behaves. But in principle, you would probably have to use different mode decompositions, because here the Hermite-Gauss modes are very good to do this kind of decomposition in the XY plane, in the transverse plane. So you would have to have modes that are sensitive also to this longitudinal direction. And this exists if you use time frequency modes. I guess you could even look at trying to determine redshifts and so on and these kind of things. So all this kind of stuff is in principle possible. So it's always a matter of choosing the right modes. Then indeed what you could do if you have, once you look at your galaxy, you could try, and then it really depends on how all the noise terms and so on work together. You have to then see what for your galaxy would correspond to with the point spread function taken into account. When you analyze all of this, what would be the smallest resolvable distance? And if this smallest resolvable distance is within the size of your galaxy, you could definitely take 2 points in the galaxy and try to say how far they are apart. Then the problem is that probably you will not have 2 points, but you will have many, many points in your image plane, and you have to take this into account, which means that there are many more parameters somehow that you have in play that you do not know. And so you have to take into account the fact that there is some signal, that some influence of parameters that you do not know, and so on. So this is multi-parameter estimation techniques then. And then the last question was like applying it really in reality. So we are now at the stage, I think, in this field. So this is something that really exploded with this work of Mankei Zhang, where they really showed that you saturate the quantum Fisher information for this problem. So it's like the best you can possibly do. And so what people are now working on is proof of principle experiments. So really, we are doing an experiment with kind of laser beams that we are trying to make thermal to test, and that we can really control how far they are and so on, to really test, does this work, how well does it work, and so on. And then I guess the next step would be to try indeed to implement this in practice. And then we would have to go and talk to astronomers, because I have high esteem of astronomers. And I wouldn't be surprised if there are some of these ideas that they already use, maybe implicitly, maybe in a very different jargon, formulated very differently. But I guess they probably have their own techniques that might also be. So you have the quantum Fisher information, which is the best noise that you can get, like the lowest noise you can get. But there is no guarantee that there is only one measurement that would saturate it. So maybe they have found another one that does it. So there are many, I don't know. So I guess we would have to really go through a serious discussion with the astronomers to understand much better the optics really that they do. And this is more something for the experimentalists than for the poor quantum optician, I would say. But yeah, that's giving you kind of an idea of the field and where we are now.
Thank you very much.
Okay, are there further?
I do have a tiny question.
Yeah, Bernardo, go ahead with your question.
Yes, please. You see, speaking about this distinction between two sources in a distant galaxy, most likely this would be stars with a different spectrum. Say one could be orange and the other one could be white.
Yes.
So is there anything you can use from those situations in non-galactic environments?
Now we're asking many questions of things. So we've worked a lot about. So one thing that I didn't really say, but what we often assume is actually that the two sources are completely identical, like that they even have the same intensity of light and so on. But this is in general indeed going to be completely like not the case. So in principle, we have all the machinery to take this into account. We're working on this also right now. It's a bit more technical issues as well. So but yeah, so one of the things that we always assume is that these two sources, that they emit, like they emit in two modes that are somehow separated in this transverse plane. But apart from that, everything is, they're kind of identical. And specifically in the time frequency degrees of freedom, we assume that they are emitting in the same mode. And so we are thinking now about this kind of questions for very different reasons. If you build an experiment, you have to take into account that when you do a measurement, that you actually measure for a finite time, you have integration times. Your light that you emit is actually not like, you assume when you do these things that you do a detection and this is like one point in time. But photons, light, it has a temporal structure. And so we are now kind of wondering about how we have to take this into account, how we can take this into account. But I would definitely say that, like, more generally speaking, adding these time frequency degrees of freedom, like, for example, different frequencies, or maybe, yeah, like even different spectra. If it's like one frequency, it's a bit boring, but like really just like they emit in a wide spectrum, and taking into account these spectral degrees of freedom and how these can be known or unknown parameters, how they influence the precision with which you can estimate things. I think this is a very interesting problem that in principle can be tackled with all the same machinery, but we haven't really done this because we would need to have good ways of modeling these sources. Like, we would need to know what the interesting spectra are to look at, to start out from, and so on, and what kind of the shapes are also of these spectra, because we use, like, the spatial modes that we use are Gaussian, but in the spectra of a star, I doubt that it's going to be a nice and Gaussian shape. So I guess there is a lot of additional stuff to take into account there, and I think this is a very interesting question, and I would expect that, like, whatever you have that makes the sources more different, like whether it's imbalance in intensity, whether it's different colors, whether it's I don't know, a different modal shape, I guess, in like a spatial structure, usually whatever makes them different will make them easier to distinguish. So I think with the frequencies, this would be the same. What would be more interesting would be somehow if you want to estimate also properties of the spectra at the same time. This might be possible as well, but then you would also have to do frequency mode demultiplexing, which is much harder than spatial mode demultiplexing because it usually requires nonlinear optics or nonlinear fibers and so on. This is experimentally tricky, but for theorists, it's not very different than spatial modes.
Okay, thank you very much, Mattia. Are there other questions, comments from the audience? Yeah, if this is not the case, Mattia, thank you very much again for joining us today virtually. Next time, I hope so, in person here again in Cuernavaca.
Yes, I hope so too. Yeah, it's thank you very much for having me. It was a real pleasure, and I hope you enjoyed the talk. And yes, I guess that's it. I would say good night, but for you, it's still a good afternoon. So.
Hey, good afternoon. We will have lunch now here. Okay.
I already had dinner, so I enjoy lunch.
Okay, and thank you very much, and yeah, to everyone, bye bye.